Stationary points. Now, stationary points are points on the curve where the gradient is zero. And I've talked about this idea of a tangent having a gradient zero being important. And this is why. Because we can find maximum points on a curve. These are called local maxima. Minimum points on a curve. And both of those are useful for something called optimization. You might want to minimize costs or maximize profits. You also get these inflection points where the gradient is zero as well. In the diagram, it's spelt with a CT. You can spell it with an X as well, and I tend to go for the X version. Okay, so we want to determine the exact coordinates of any stationary points on this curve given here. So we need dy dx, but before we leap into that, what we have here is a product. Don't worry about the 150, that's just going to differentiate away to 0. So u is x minus 4 cubed, and v is x plus 4. So du dx, chain rule, but the differential of the inside is 1, so that's not a problem. 3x minus 4 squared, and dv dx is just 1. So dy dx is going to be v du dx, so that's 3x plus 4 x minus 4 squared plus u dv dx, which is x minus 4 cubed. Now we might want to do some factorising here. X minus 4 squared comes out, and what we would be left with is 3x plus 4 add x minus 4, which gives us x minus 4 all squared, and then here we've got 3x plus another x, that's 4x. 12 take away 4, so that's plus 8. So we could take a 4 out of that lot and have 4x minus 4, x plus 2. Now we're interested for stationary points in where dy dx is equal to 0. So that means 4x minus 4 x plus 2 is equal to 0, and just like when you're solving a quadratic, that means x equals 4 or x equals negative 2. Now it does say coordinates, so x equals 4 means that y equals, well, if x is 4, this term here just becomes 0, so it's going to be 150. So we have 4, 150. And we'll come to determine the nature in a moment. And when x is negative 2, y is going to be, so what would we have there? If it's negative 2, we'll have negative 6 cubed multiplied by 4, add 150. So we just need to calculate that. So I've got negative 6 cubed, that's going to be negative 216 multiplied by, so x was negative 2, that was actually 2 then, just there. So we need to multiply that by 2 and then add 150. That gives me negative 282. I'm just going to check that since I made that mistake. So we've got negative 2, negative 282. And so let's just see if x is negative 2. Get negative 6 cubed from that first bracket, and then 2, and then add 150. Yep, that's okay. So, determine the nature. Right. So what I'm going to do here, let's just make a little bit of space down here. So there's several ways of determining the nature, and one of them is to use the second derivative, and that's the way I'm going to do this one, or at least I'm going to try to do this one. And I'll discuss the second derivative rule while we're doing it. So it's probably best for me to go from that line, and I want the second derivative, d2y dx squared. Now, if we think about this one, it's a product. So I'm running short of space here, but let's have u is equal to 3x plus 4, and v equals x minus 4 squared. So du dx is going to be 3, and dv dx is going to be twice x take 4. So v du dx is 3 x minus 4 squared, and u dv dx is going to give me 6 x plus 4 x minus 4. Now d2y dx squared, given that x is equal to 4, well, that's going to be 0, and that's going to give us a problem. So we're going to return to that one in a minute. d2y dx squared, given that x is equal to negative 2, so what's that going to give me? It's going to give me 3 times negative 2 squared. Sorry, negative 6 squared if I put negative 2 in there. So negative 6 squared is 36. 3 times that's 108. And then that's going to be add 6 times 2 times negative 6, which is negative 72. So in actual fact, that's equal to 36, which is positive. And when the second derivative is positive, that implies that we have a minimum point. So this one here is a min. So that's the nature of that particular point. If we get one that's negative, that tells us we have a maximum. The problem is when we get a 0, because it doesn't tell us anything at all. And we have to use another method when that is the case. Now that's probably why I left all this space down here on the next page. I've been trying to do it all in one place at the moment. Now, so we've got second derivative coming to 0. So what I need to do now is go back to the first decimal place. First derivative. So dy dx was equal to 3 x plus 4 x minus 4 or squared plus x minus 4 cubed. And we do something called a sign table. So we found that dy dx was 0 when x was 4. So what I want to do is take a point to the left of that and a point to the right, and we'll see what happens to dy dx at those points. Now I could take any point to the left, any point to the right, as long as I don't go past another stationary point. In other words, as long as I don't go to the left of negative 2, I'd be absolutely fine. And I've only gone down as far as 3, so that's all good. Okay, so what we're going to have to do is calculate, well, we know dy dx is 0 there. That's the whole reason we're doing this method. So, what do we have? X is 3, so it's going to be 3 multiplied by 3 plus 4, which is 7, multiplied by 3 take away 4, which is negative 1 squared, so that's just actually times 1, add 3 take away 4, negative 1 cubed, so actually that's going to just be negative 1 and that's 20. It really doesn't matter that it's 20. The whole point is it's positive. If we go to 5, what do we get? So I'm just going to go and adjust this. So we've got 3 times, so it'll be 5 plus 4, which is 9. And then 5 take away 4 is 1. Square that, so that's still 1. 5 take away 4 is 1. 1 cubed, so that's going to be just plus 1. I'll just do minus minus 1. It will give me the same thing. And that's 28. And the important thing is that that's positive. So if we think about what happens to the curve, it's got a positive gradient, then a 0 gradient, then a positive gradient. So the curve is going like that. So that tells us that we have a point of inflection. So we have a horizontal point of inflection at 150. Now it's quite a long video already, this, more than 10 minutes. It's quite a complicated expression as a sort of first example on this. But the important thing is that finding a turning point means putting dy dx equal to 0, and we managed to find the points from there. You can test the nature of a turning point by looking at the second derivative. If the second derivative as it is here is positive, that tells you have a minimum. If it's negative, you have a maximum. But if it's 0, it doesn't tell you anything. It turned out to be a point of inflection this time, but it could just as easily give you d2y dx squared equals 0 and give you a minimum or a maximum. So you have to be careful, and therefore we go and use the sine table. And the sine table is based on dy dx because that's the gradient function. So we know that the curve is going positive in this case, then 0, then positive, and that's a horizontal point of inflection.